Our universe is a vast and mysterious place, filled with wonders that boggle the mind and stretch the limits of our understanding. Full of stars, galaxies, and planets, each one a world unto itself, each one a piece of the grand cosmic puzzle, stretching out farther than we can possibly imagine, beyond the reach of our most powerful telescopes and the grasp of our wildest dreams. But have you ever wondered where it all began? What sparked the creation of this magnificent universe? How did this incredible cosmos we call home come to be? What forces shaped the stars and galaxies that light up our night sky? The answer, my friends, lies in the depths of time, in an event we call the Big Bang. This monumental occurrence set everything into motion. The Big Bang wasn't an explosion that happened somewhere in space. It was the expansion of space itself, an event so profound that it marked the very beginning of time as we know it. Imagine, if you will, a moment when time and space were born together. A singular instant that gave rise to everything we see and know. Imagine, if you will, the entirety of our universe, everything we see and know, compressed into a point smaller than an atom. A point of infinite density and temperature. This, my friends, is the singularity. From this tiny, unimaginable point, our universe began its grand expansion, unfolding the fabric of space and time. Over billions of years, this expansion gave birth to galaxies, stars, and planets, creating the vast and intricate cosmos we explore today. And so, as we gaze up at the night sky, we are looking back in time, witnessing the echoes of that ultimate beginning. The story of our universe is a tale of wonder and discovery, a journey that began with the Big Bang and continues to unfold with each passing moment. Join us as we delve deeper into this cosmic adventure, exploring the mysteries of the universe and our place within it. The singularity is a concept that stretches our minds to their limits. It was a point of infinite density and temperature, a place where the laws of physics as we know them break down. Imagine all the matter and energy in the universe squeezed into an infinitesimally small point. It's mind-boggling, isn't it? This singularity wasn't just sitting there doing nothing, it was a cauldron of unimaginable energy, a cosmic egg waiting to hatch. And then, something incredible happened. The universe, in a fraction of a second, began to expand, and it kept expanding, faster than the speed of light, in an event we call cosmic inflation. Picture, if you will, a tiny subatomic speck, smaller than anything you can possibly imagine. Yet, this infinitesimal point contained the blueprint for everything that is, was, and ever will be in our universe. This is the singularity, the seed of the cosmos. Now, imagine that seed suddenly bursting forth, not in an explosion outwards, but in an expansion of space itself. The very fabric of reality stretched and unfolded, carrying with it the raw ingredients of stars, galaxies, and planets. This, my friends, was the Big Bang. The Big Bang wasn't your typical explosion, like fireworks on the 4th of July. It wasn't a burst of light and sound from a single point. Instead, it was the expansion of space itself, a stretching of the cosmic fabric in all directions simultaneously. Imagine the entire universe as a vast elastic sheet being pulled apart. Imagine a balloon with dots drawn on it. These dots represent galaxies. As you inflate the balloon, the dots don't explode outwards from a central point. They move apart from each other as the balloon itself expands. This is similar to how galaxies move apart as the universe expands. As space expanded, it cooled, allowing energy to convert into matter according to Einstein's famous equation, E equals mc squared. This cooling process was crucial for the formation of the universe as we know it. This wasn't just any matter. It was the building blocks of everything we see around us. Protons, neutrons, electrons. These particles began to form within the first few minutes of the Big Bang. The universe was coming alive. Over time, these particles combined to form atoms, which eventually led to the formation of stars and galaxies. The cosmos was evolving, setting the stage for everything we observe today. From the fiery birth of stars to the swirling dance of galaxies, the universe continued to expand and evolve. Planets began to take shape, and the stage was set for the emergence of life. On one of these planets, Earth, life began to flourish. From simple microorganisms to complex ecosystems, the journey from the Big Bang to the present day is a story of constant change and evolution. And as we look up at the night sky, filled with countless stars, we are reminded of the incredible journey that began with a single cosmic event. The Big Bang was not just the beginning of space and time, but the dawn of everything we know and love. Section 5. The Great Inflation. In the first fleeting fractions of a second after the Big Bang, something extraordinary occurred: cosmic inflation. This was a period of extremely rapid expansion where the universe grew exponentially in size in an unimaginably short amount of time. Imagine a universe smaller than an atom suddenly ballooning to an astronomical size, far faster than the speed of light. This expansion was so rapid that it defies our everyday understanding of speed and distance. This mind-bending expansion, driven by an unknown force, smoothed out the fabric of space-time and sowed the seeds for the large-scale structures we observe today. It was as if the universe was being ironed out, removing any initial irregularities and creating a smooth, uniform cosmos. Think of a loaf of raisin bread dough rising in the oven. As the dough expands, the raisins, which represent galaxies, move further apart from each other. The raisins, representing galaxies, spread apart as the dough, representing space, expands. This analogy helps us visualize how galaxies are distributed throughout the universe as it continues to expand. Cosmic inflation stretched out any initial wrinkles in the universe, making it remarkably uniform on large scales. This uniformity is crucial for the formation of galaxies, stars, and planets, as it provided a stable foundation for the cosmic structures we see today. The remnants of this inflationary period can still be observed today in the cosmic microwave background radiation, which is a faint glow left over from the early universe. These primordial fluctuations are the fingerprints of the Great Inflation, offering us a glimpse into the universe's earliest moments. Modern telescopes and deep space observations allow us to map the universe and study these ancient signals, helping us understand the profound impact of the Great Inflation on the cosmos. This period set the stage for everything that followed, shaping the universe as we know it. Section 6. From Chaos to Cosmos. Initially, the universe was a chaotic soup of elementary particles, a seething inferno of energy and matter constantly colliding and interacting. But as the universe continued to expand and cool, these particles began to combine, forming the first atoms, primarily hydrogen and helium. Imagine a dance floor filled with individuals moving erratically. As the music slows and the lights dim, these individuals begin to partner up, forming more ordered pairs. Similarly, the cooling universe allowed particles to combine, creating the building blocks of stars and galaxies. Section 7. Echoes of Creation. The universe wasn't done revealing its secrets just yet. As we gazed deeper into space, we discovered a faint afterglow, a cosmic microwave background radiation, bathing the universe in a faint whisper of its fiery birth. This radiation, discovered in the 1960s, is like a baby picture of the universe, providing a glimpse into its infancy. Imagine a bonfire on a chilly night. Even after the flames have died down, the warmth lingers in the air. Similarly, the cosmic microwave background radiation is the residual heat from the Big Bang, a faint but pervasive echo of creation. Section 8. The Expanding Universe, a mind-bending concept. The universe's expansion isn't like an explosion scattering debris outward. It's the very fabric of space itself that's stretching, carrying galaxies along for the ride. Imagine dots drawn on a balloon. As you inflate the balloon, the dots don't move across the surface. They move apart from each other as the balloon's surface expands. This expansion has profound implications. It means that distant galaxies are moving away from us, and the farther away they are, the faster they seem to be receding. It's a mind-bending concept, but it's a cornerstone of modern cosmology. Section 9. A Universe of Wonder. The Big Bang and cosmic inflation aren't just abstract theories. They're supported by a wealth of observational evidence. From the cosmic microwave background radiation to the abundance of light elements in the universe, the evidence points to an extraordinary beginning for our cosmos. The universe is a vast and awe-inspiring place, and the more we learn about its origins, the more we realize how much more there is to discover. Section 10. Our Cosmic Address, a Humble Perspective. As we contemplate the vastness of the universe, it's humbling to consider our place in it. We live on a small planet orbiting an average star in a galaxy among billions. Yet, we are part of this grand cosmic story, a product of the Big Bang and the extraordinary chain of events that followed. The universe is still expanding, evolving, and full of mysteries waiting to be unraveled. So keep looking up at the night sky with wonder and curiosity, for the cosmos has many more stories to tell.
The Big Bang theory is our best model of the universe's beginning. It provides a comprehensive explanation of how the universe expanded from a hot, dense state into the vast cosmos we observe today. Imagine the universe starting from an infinitesimally small point, smaller than the smallest atom, containing everything that is, was, and ever will be. This singularity held all the matter, energy, and even the laws of physics that govern our universe. Then imagine this point expanding outward. Not an explosion in space, but an expansion of space itself. This expansion was incredibly rapid, transforming the universe from a minuscule point to a vast expanse in a fraction of a second. This rapid expansion in the first fraction of a second after the Big Bang is known as inflation. During this brief period, the universe grew exponentially faster than the speed of light. Inflation is crucial because it explains why the universe looks the way it does today. It accounts for the large-scale structure of the cosmos and the uniformity we observe in the cosmic microwave background radiation. It stretched out the fabric of space-time, smoothing out any initial irregularities and leaving behind a universe that is remarkably uniform on the larger scales. This smoothing effect is why the universe appears so homogeneous and isotropic. But what happened after this initial burst of inflation? The universe continued to expand and cool, leading to the formation of particles, atoms, stars, and galaxies. This set the stage for the complex and diverse universe we see today, filled with countless galaxies, each containing billions of stars. Let's rewind the clock to a time just 10 to the power of negative 32 seconds after the Big Bang. At this moment, the universe was incredibly hot and dense, much hotter and denser than the core of any star we know today. To give you an idea of the scale, imagine squeezing all the matter in the observable universe into a volume smaller than an atom. This incredibly dense and energetic environment was not a place for atoms or even the particles that make up atoms. Instead, it was a seething cauldron of fundamental particles, a primordial soup of the universe's building blocks. The universe at this time was dominated by a plasma of quarks, gluons, and other fundamental particles. This state of matter existed just moments after the Big Bang, when the universe was incredibly hot and dense. The Quark-Gluon Plasma was a seething, energetic soup where the building blocks of matter were free to move and interact. Quarks are the elementary particles that make up protons and neutrons, which in turn make up the nuclei of atoms. There are 6 types of quarks known as flavors: up, down, charm, strange, top, and bottom. The most common quarks in the universe are the up and down quarks, which combine to form protons and neutrons. Gluons, on the other hand, are the force carriers responsible for the strong force, one of the 4 fundamental forces in nature. This force is incredibly powerful, but it acts only over very short distances, binding quarks together within protons and neutrons. The strong force binds quarks together to form protons and neutrons. Without this force, the quarks would not be able to stay together, and the fundamental structure of matter as we know it would not exist. This plasma was not just a random collection of particles, it was a highly interactive and dynamic state of matter, where quarks and gluons were constantly in motion, colliding and exchanging energy. It was a dynamic and chaotic environment where particles constantly collided and interacted with each other at incredibly high energies. These interactions were so intense that they could create new particles and destroy existing ones in a continuous cycle. These collisions created and destroyed particles in a continuous dance of energy and matter. This dance was fundamental to the evolution of the early universe, setting the stage for the formation of more complex structures, such as atoms, stars, and galaxies. One of the most intriguing aspects of the early universe was its opacity. In the first few 100,000 years after the Big Bang, the universe was not transparent to light. The photons, or particles of light, were constantly being scattered by the free electrons in the plasma, much like light scattering through fog. This constant scattering prevented light from traveling freely through space. If you were somehow able to exist in this early universe, you wouldn't be able to see anything around you. The universe would be a glowing, opaque fog. Section 5. Matter and Antimatter, a cosmic dance of destruction. Another fascinating phenomenon that occurred in the early universe was the annihilation of matter and antimatter. Antimatter is made up of antiparticles, which have the same mass as their corresponding matter particles but opposite charge. When a matter particle and its antimatter counterpart meet, they annihilate each other in a burst of energy. In the extremely hot and dense conditions of the early universe, matter and antimatter particles were constantly being created and destroyed in equal amounts. These annihilation events released enormous amounts of energy, further contributing to the intense heat of the early universe. Section 6. The matter-antimatter imbalance, a fortunate asymmetry. However, there was a slight imbalance in the amount of matter and antimatter. For every billion antimatter particles, there were about 1,000,001 matter particles. This tiny asymmetry had profound consequences. As the universe expanded and cooled, most of the matter and antimatter annihilated each other, leaving behind a small surplus of matter. This surplus of matter is what makes up everything we see in the universe today, from stars and galaxies to planets and people. Without this slight imbalance, the universe would be a very different place, filled only with radiation and devoid of the structures we observe. Section 7. From plasma to particles, the cooling universe. As the universe continued to expand, it also cooled. Around 1 second after the Big Bang, the temperature had dropped enough for quarks to combine and form protons and neutrons, the building blocks of atomic nuclei. This marked a crucial transition in the early universe, as the primordial plasma began to transform into a sea of particles. This cooling also meant that the energy of photons decreased. Eventually, the photons no longer had enough energy to prevent the formation of neutral atoms, leading to a transparent universe. Section 8. The formation of hadrons, protons, and neutrons emerge. With the cooling of the universe, a crucial event occurred. Quarks, which had been freely roaming in the hot plasma, began to combine to form hadrons. Hadrons are composite particles made up of quarks held together by the strong force. The most familiar hadrons are protons and neutrons, the building blocks of atomic nuclei. The formation of hadrons marked a significant step in the evolution of matter in the universe. It paved the way for the eventual creation of atoms, the building blocks of stars, galaxies, and ultimately life itself. Section 9. The cosmic microwave background, a baby picture of the universe. Around 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and neutrons to form neutral atoms, primarily hydrogen. This cooling period was crucial because it allowed the universe to transition from a hot, dense state to a more stable and structured form. The formation of these neutral atoms was a significant milestone in the evolution of the cosmos. This event, known as recombination, had a profound effect on the universe. During recombination, the charged particles that once scattered light were now bound together, allowing light to travel freely. This process fundamentally changed the dynamics of the universe, setting the stage for the formation of galaxies and other cosmic structures. It marked the time when the universe became transparent to light. Before recombination, the universe was opaque, much like a dense fog. But as neutral atoms formed, the fog lifted and the universe became clear, allowing light to pass through unimpeded. The photons that were once trapped in the hot, dense plasma were now free to travel through space. These photons began their journey across the cosmos, carrying with them a snapshot of the universe at that early time. These photons, stretched out over billions of years of cosmic expansion, formed the cosmic microwave background radiation, a faint afterglow of the Big Bang that we can still detect today. This radiation provides us with a wealth of information about the early universe, offering clues about its composition, structure, and evolution. By studying the cosmic microwave background, scientists can piece together the history of the universe, from its fiery beginnings to its current state. Section 10. The importance of the primordial universe. Understanding the conditions and events of the primordial universe is crucial for unraveling the mysteries of our cosmic origins. By studying the remnants of this early epoch, such as the cosmic microwave background radiation and the abundance of light elements, cosmologists can piece together the history of the universe and test our current theories about its evolution. The study of the primordial universe provides a fascinating glimpse into the extreme conditions that existed just moments after the Big Bang. It helps us understand how the fundamental particles and forces of nature interacted to create the universe we observe today. Section 11. Conclusion, looking back to understand our beginnings. The period after inflation, particularly the first few seconds to minutes after the Big Bang, played a pivotal role in shaping the universe we inhabit. It was a time of extreme conditions, unimaginable energies, and fundamental transformations that set the stage for the formation of stars, galaxies, and life itself. As we continue to probe the mysteries of the cosmos, understanding the primordial universe remains a key goal for cosmologists. By studying this early epoch, we gain a deeper appreciation for the intricate workings of the universe and our place within its grand cosmic narrative.
Imagine a universe smaller than an atom, unimaginably hot and dense. This was the state of our universe a mere fraction of a second after the Big Bang. Then, the universe began to expand and cool rapidly, a period we call inflation. This expansion marked the beginning of the universe as we know it. It set the stage for the formation of stars, galaxies, and ultimately life itself. Around 10 to the power of minus 43 seconds after the Big Bang, the universe had cooled to a still unfathomable 10 to the power of 32 Kelvin. Gravity, the first of the four forces, became distinct. As the universe expanded and cooled, the strong force separated from the unified force. The strong force, incredibly powerful, operates over short distances within the nucleus of an atom. This separation was crucial for the formation of matter. While the strong force was busy binding quarks, gravity was hard at work on a larger scale. The tiny quantum fluctuations in the early universe, amplified by the rapid expansion, provided the seeds for what would become the large-scale structure of the cosmos. Imagine a perfectly smooth tablecloth. Now, sprinkle some grains of sand onto it. These grains represent the slightly denser regions of the early universe. Gravity, like an invisible hand, gently tugged at the tablecloth around these grains, causing the fabric to bunch up. Over billions of years, this gentle tugging created a universe where matter is not evenly distributed but instead clumps together in vast cosmic structures. These clumps of matter eventually evolved into the galaxies and galaxy clusters we observe today, interconnected by a vast cosmic web. Gravity's influence on the large-scale structure of the universe is a testament to its patient and persistent nature. Even though it is the weakest of the four fundamental forces, its reach is limitless, shaping the cosmos over vast distances and eons. The strong force plays a crucial role in the universe. It binds quarks, those fundamental particles, to form protons and neutrons. Imagine quarks as tiny, energetic marbles constantly jiggling and bouncing around. The strong force acts like a powerful glue, holding these quarks together to form the protons and neutrons that reside at the heart of every atom. But the strong force is a bit unusual. Unlike gravity, which weakens with distance, the strong force actually gets stronger as quarks get farther apart. Think of it like a spring. The more you stretch it, the harder it pulls back. This unique property ensures that quarks are always confined within protons and neutrons, forming the stable building blocks of matter. The formation of protons and neutrons was a pivotal moment in the universe's history. These particles would eventually combine to form the first atoms, primarily hydrogen and helium, paving the way for the formation of stars and galaxies. Section 5, a universe of quarks, the tiniest particles, take center stage. At this incredibly early stage of the universe, approximately 1/1,000,000th of a second after the Big Bang, the universe was a hot, dense soup of quarks, gluons, and other fundamental particles. This Quark-Gluon Plasma was like a cosmic pressure cooker, with temperatures reaching a mind-boggling 10 quadrillion degrees Kelvin, or 180 million trillion degrees Fahrenheit. Imagine a universe so hot that even atoms couldn't exist. Quarks, the building blocks of protons and neutrons, roamed freely in this extreme environment, constantly colliding and interacting with each other. Gluons, the force carriers of the strong force, mediated these interactions, effectively gluing quarks together. This Quark-Gluon Plasma is a state of matter that no longer exists naturally in the universe. However, scientists have recreated this exotic state in particle accelerators like the Large Hadron Collider, providing valuable insights into the conditions of the early universe. Section 6. The weak force makes its debut, a force of transformation. While the strong force was binding quarks, and gravity was shaping the universe's structure, the weak force was busy with its own crucial role transforming particles. The weak force is responsible for radioactive decay, a process where unstable particles transform into more stable ones. Imagine baking a cake. The heat transforms the batter, causing its ingredients to undergo chemical changes, and ultimately form a delicious treat. Similarly, the weak force acts as a catalyst for change in the quantum world, transforming particles and shaping the composition of the early universe. For example, the weak force is responsible for the decay of neutrons into protons, emitting an electron and an antineutrino. This process is crucial for the balance of protons and neutrons in the universe, ultimately affecting the formation of elements and the evolution of stars. Section 7. Electromagnetism, lighting up the cosmos. The final force to emerge, at around 10 to the power of -12 seconds after the Big Bang, was electromagnetism. This force is responsible for the interactions between electrically charged particles, governing everything from the behavior of atoms and molecules to the propagation of light. Imagine a world without light, without the warmth of the sun, or the vibrant colors we see around us. This is a world without electromagnetism. This force is responsible for the electromagnetic spectrum, which includes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Electromagnetism is also responsible for the chemical bonds that hold atoms together in molecules. Without it, atoms would not bond to form the complex molecules that make up living organisms and everything around us. Section 8. A symphony of forces, the interplay that shapes our universe. The four fundamental forces, though distinct, work together in a delicate and intricate dance to shape the universe we observe. Gravity, the architect, sculpts the large-scale structure of the cosmos, pulling together galaxies and galaxy clusters. The strong force, the master builder, binds quarks into protons and neutrons, forming the hearts of atoms. The weak force, the transformer, governs radioactive decay, influencing the balance of elements in the universe. Finally, electromagnetism, the illuminator, lights up the cosmos, governs chemical bonds, and enables the propagation of light. Imagine a symphony orchestra, with each instrument playing its part to create a harmonious melody. Similarly, the four fundamental forces, each with its own unique characteristics and strengths, work in concert to create the complex and diverse universe we inhabit. This interplay of forces is essential for the existence of stars, planets, and ultimately life itself. It is through their combined influence that the universe has evolved from a hot, dense soup of particles to the complex and awe-inspiring cosmos we observe today. Section 9. Echoes of the Big Bang, evidence of the early universe. While we can't turn back time to witness the birth of the universe and the separation of the fundamental forces, we can observe echoes of these early events. The cosmic microwave background radiation, a faint afterglow of the Big Bang, provides a snapshot of the universe just 380,000 years after its birth. Imagine looking at a distant star. The light we see from that star has traveled for millions, even billions of years to reach our eyes. Similarly, The cosmic microwave background is like a cosmic message from the early universe, carrying information about the conditions that existed when the universe was young. The patterns and temperature fluctuations in the cosmic microwave background provide valuable clues about the early universe's composition, expansion rate, and the interactions of fundamental forces. Studying the cosmic microwave background is like piecing together a cosmic jigsaw puzzle, revealing the secrets of the universe's earliest moments. Section 10. The Ongoing Journey, Unveiling the Mysteries of Our Cosmic Origins. The story of the universe's birth and the separation of the fundamental forces is a testament to the power of scientific inquiry. Through observation, experimentation, and theoretical modeling, we have been able to piece together a remarkable narrative of our cosmic origins. Yet, many mysteries remain. The nature of dark matter and dark energy, the unification of gravity with the other fundamental forces, and the possibility of other universes are just a few of the questions that continue to drive scientific exploration. Like explorers charting unknown territories, scientists are constantly pushing the boundaries of our understanding, seeking answers to the universe's most profound questions. The journey to comprehend our cosmic origins is ongoing, fueled by curiosity, ingenuity, and a deep-seated desire to unravel the mysteries of the universe we inhabit.
Imagine a time when our entire universe was smaller than an atom. It was unimaginably hot and dense. Then, in a fraction of a second, everything changed. The universe exploded outwards in an event we call the Big Bang. This wasn't your typical explosion, like fireworks on the 4th of July. Instead, it was the rapid expansion of space itself. As the universe expanded, it cooled, setting the stage for the creation of everything we see today. But before stars, galaxies, or even atoms, the universe was a chaotic soup of fundamental particles. This primordial soup held the ingredients for everything in the cosmos. Let's dive in and see how these ingredients combine to form the light elements that make up our universe. In the first few minutes after the Big Bang, the universe was incredibly hot, reaching trillions of degrees. At these temperatures, matter couldn't exist as we know it. Instead, space was filled with a sea of fundamental particles. Two of the most important particles were protons and neutrons. Protons with a positive charge would eventually form the heart of atoms. Neutrons with no charge would join them in the atomic nucleus. But the universe was a turbulent place. Protons and neutrons constantly collided with each other at incredible speeds. These collisions were too violent for them to stick together and form anything larger. The universe needed to cool down for the next stage of creation to begin. As the universe expanded, it cooled like a pot of boiling water coming off the stove. Around 1 second after the Big Bang, the temperature dropped enough for a remarkable process to begin. The strong nuclear force could now take hold. Think of the strong force as a cosmic glue, much stronger than the electrical forces we experience every day. This powerful glue could bind protons and neutrons together, overcoming their natural tendency to repel each other. The universe had become a cosmic pressure cooker. Protons and neutrons, squeezed together in the hot, dense soup, began to fuse and form the first atomic nuclei. This process is what we call Big Bang nucleosynthesis. The first element to form in the Big Bang was the simplest and most abundant in the universe, hydrogen. A single proton, alone in the early universe, is essentially a hydrogen nucleus. But the cosmic pressure cooker didn't stop there. Protons and neutrons continued to collide and fuse, forming heavier nuclei. One proton and one neutron, bound together by the strong force, created deuterium, a heavy isotope of hydrogen. Two protons and two neutrons, a stable configuration, formed the nucleus of helium, the second most abundant element in the universe. These light elements, forged in the first few minutes of existence, would become the building blocks for stars, galaxies, and even life itself. Section 5. The clock is ticking. The formation of light elements in the early universe was a race against time and temperature. In those first few moments, conditions were just right for the creation of the simplest elements. As the universe expanded and cooled, the energy required for nuclear fusion decreased. This cooling process was crucial as it determined which elements could form and which could not. Around 3 minutes after the Big Bang, the temperature had dropped to about 1 billion degrees. This rapid cooling was a pivotal moment in the universe's history. This may sound incredibly hot, but it wasn't hot enough for further nuclear reactions to occur at a significant rate. The universe was cooling too quickly for heavier elements to form. The window for Big Bang nucleosynthesis had closed. The conditions necessary for the formation of new elements were no longer present. The universe was now filled with a specific ratio of light elements, a fingerprint of those first few minutes of creation. Hydrogen and helium dominated this early elemental mix. But what about heavier elements, like carbon, oxygen, and iron? These elements were not formed in the early universe. Their story would have to wait for the formation of stars, the cosmic furnaces that would forge these heavier elements much later in the universe's history. Stars would become the factories where these heavier elements were created through nuclear fusion. Section 6. A dash of deuterium and a pinch of lithium. While hydrogen and helium dominated the early universe, trace amounts of other light elements also formed during Big Bang nucleosynthesis. Deuterium, the heavy isotope of hydrogen, continued to form through reactions involving protons and neutrons. Another light element, lithium, with 3 protons and 4 neutrons in its nucleus, also appeared in minute quantities. These trace elements, while rare compared to hydrogen and helium, play crucial roles in the evolution of stars and galaxies. The precise abundance of these light elements, as measured by astronomers today, provides strong evidence for the Big Bang theory. The observed ratios of hydrogen, helium, deuterium, and lithium match the predictions of Big Bang nucleosynthesis remarkably well, offering a glimpse into the universe's earliest moments. Section 7. The universe cools down. With the formation of light elements complete, the universe continued to expand and cool. The once raging inferno gradually transformed into a vast, dark expanse dotted with the embers of creation. The newly formed atomic nuclei. Electrons, much lighter than protons and neutrons, still zipped around in a high-energy frenzy. But as the universe cooled further, these electrons began to slow down. The universe was preparing for another momentous event, the formation of the first atoms. Around 380,000 years after the Big Bang, the temperature had dropped to a few thousand degrees. Electrons, now moving slowly enough, could be captured by the positively charged nuclei. This capture formed the first neutral atoms of hydrogen and helium, filling the universe with a diffuse, glowing gas. Section 8. Echoes of the Big Bang. The formation of neutral atoms had a profound effect on the universe, marking a pivotal moment in cosmic history. Before this time, light couldn't travel freely, as it was constantly scattered by the dense plasma. The universe was a hot, opaque plasma where photons, the particles of light, constantly collided with charged particles, creating a fog-like environment. But with the formation of neutral atoms, the universe underwent a dramatic transformation and became transparent. Photons could now travel unimpeded across vast distances, illuminating the cosmos. This first light, released when the universe was about 380,000 years old, is still detectable today as the cosmic microwave background radiation, a relic of the early universe. This faint afterglow of the Big Bang provides a snapshot of the universe in its infancy, offering a glimpse into its earliest moments. By studying the cosmic microwave background, astronomers can learn about the conditions present just a few 100,000 years after the Big Bang, providing further confirmation of this remarkable event and deepening our understanding of the universe's origins. Section 9. The cosmic recipe for life. The formation of light elements in the first few minutes after the Big Bang wasn't just a cosmic curiosity. It was a crucial step in the chain of events that led to the formation of stars, galaxies, planets, and ultimately, life itself. Hydrogen, the most abundant element, would fuel the nuclear fusion reactions in stars, forging heavier elements in their cores. These heavier elements, dispersed into space when stars exploded as supernovae, would become the building blocks for planets and everything on them. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were created in the hearts of stars, their origins tracing back to the Big Bang and the formation of light elements in those first few minutes of existence. Section 10. A Universe of Possibilities. The Big Bang. Nucleosynthesis, a brief but incredibly important period in the universe's history, set the stage for everything we see around us today. This monumental event, occurring just moments after the Big Bang, led to the formation of the first light elements, such as hydrogen and helium. From the vast cosmic web of galaxies to the intricate molecules of life, it all started with the formation of light elements in the crucible of the early universe. These elements eventually coalesced to form stars, galaxies, and ultimately, the building blocks of life itself. As we continue to explore the cosmos and unravel its mysteries, we gain a deeper appreciation for the interconnectedness of everything. Each discovery, whether it be a distant exoplanet or a new type of particle, adds to our understanding of the universe and our place within it. The atoms in our bodies are literally stardust, forged in the fiery furnaces of stars long gone. These stars, through their life cycles, created the heavier elements that make up planets, plants, animals, and even us. And as we look up at the night sky, filled with billions upon billions of stars, we are reminded that our universe is a place of endless possibilities, born from the simplest of beginnings. Each star, each galaxy, holds secrets waiting to be discovered. The journey from the Big Bang to the emergence of life is a testament to the awe-inspiring power and elegance of the cosmos. It is a story of transformation, from chaos to order, from simplicity to complexity, and it continues to unfold with every passing moment. Imagine a time when the universe was young, just a baby taking its first breaths. This was a period of incredible transformation, where the very fabric of space and time was being woven together. It was a time of immense heat and energy, where temperatures soared to unimaginable heights and the energy levels were off the charts. This was a time before stars and galaxies, before the twinkling lights that now dot our night sky. The universe was a vast, empty expanse, waiting to be filled with the wonders we see today. This era is known as the Cosmic Dark Age, a period shrouded in mystery and darkness, where the universe was devoid of the light we now take for granted. This era began about 380,000 years after the Big Bang, that cataclysmic event that brought our universe into existence. The Big Bang was a moment of unimaginable power, a singularity that expanded to create everything we know. The Big Bang filled the cosmos with a scorching hot soup of particles, a primordial mix that would eventually give rise to the complex structures we see today. It was a chaotic mix of protons, neutrons, and electrons, all swirling together in a high-energy dance. These particles were the building blocks of matter, the fundamental components of the universe. As the universe expanded, it began to cool, and the particles within it started to slow down. This cooling process was essential, as it allowed the particles to come together and form more complex structures. This cooling was crucial for the formation of atoms, the building blocks of everything we see around us today. Atoms are the foundation of matter, and their formation marked a significant milestone in the evolution of the universe. But before atoms could form, the universe had to pass through a period of darkness. This was a time when the universe was still cooling, and the particles had not yet come together to form atoms. It was a time of anticipation, a prelude to the birth of the first stars and galaxies. Eventually, the universe emerged from this darkness as the first stars began to form. These early stars were the beacons of light that pierced through the cosmic darkness, heralding a new era of light and structure. With the formation of stars, galaxies began to take shape, and the universe was filled with light and structure. This marked the end of the Cosmic Dark Age, and the beginning of a new chapter in the history of the cosmos. Today, we look up at the night sky and see the legacy of these early events. The stars, galaxies, and cosmic wonders we observe are all a testament to the incredible journey the universe has taken from darkness to light. Picture a balloon inflating. As you blow air into it, the balloon expands in all directions. The universe expanded in a similar way, stretching out and becoming less dense over time. This expansion caused the universe to cool down. Think about how a hot cup of coffee cools faster when you pour it into a larger mug. The heat spreads out over a larger area, causing the overall temperature to drop. As the universe cooled, the energy of the particles within it decreased. This cooling was essential for the next stage in the universe's evolution, the formation of atoms. The early universe was not a dark, empty void. Instead, it was filled with a dense plasma, a sea of charged particles constantly interacting with light. Photons, the particles that make up light, were constantly colliding with the charged protons and electrons. These collisions prevented light from traveling freely, similar to how fog scatters light and makes it difficult to see. This interaction between light and matter trapped the photons, making the universe opaque. It was a time when light could not shine through the dense plasma, a time of darkness. As the universe continued to cool, a crucial event occurred: recombination. Protons, with their positive charge, began to capture negatively charged electrons. This union of protons and electrons formed the first atoms, primarily neutral hydrogen atoms. Hydrogen, the simplest element, became the most abundant element in the universe. Recombination marked a turning point in the universe's history. With the formation of neutral atoms, the fog began to lift. The universe was about to enter a new era, an era of light. Section 5. The universe awakens. With the formation of neutral hydrogen, the universe became transparent. Photons, no longer scattered by charged particles, were free to travel through space. This release of light marked the end of the cosmic dark age and the beginning of the epoch of reionization. The universe was bathed in the afterglow of the Big Bang, a faint glow that can still be detected today as the cosmic microwave background radiation. The universe was no longer a sea of darkness. Light could now travel freely, illuminating the vast expanse of space. Section 6. Echoes from the Dark Age. The cosmic dark age may seem like a time lost in the distant past, but it has left behind faint echoes that astronomers are only beginning to detect. These echoes come in the form of radio waves emitted by neutral hydrogen atoms during the dark ages. By studying these radio waves, astronomers hope to learn more about the distribution of matter in the early universe. These faint whispers from the dark ages hold clues to the formation of the first stars and galaxies, the structures that would eventually light up the cosmos. Section 7. Mapping the Cosmic Dawn. Astronomers are building new telescopes and developing sophisticated techniques to map the universe during and after the cosmic dark age. These instruments will allow us to peer deeper into the universe's past, observing the first stars and galaxies as they formed. By studying these early objects, we can learn more about the processes that shaped the universe we see today. The study of the cosmic dawn is a frontier of astronomy, promising to reveal new insights into the evolution of the universe. Section 8. Unlocking the Secrets of the Dark Age. The cosmic dark age may seem like a time of obscurity, but it was a crucial period in the universe's history. This era, often overlooked, holds the key to understanding the very fabric of our cosmos. It was during this era that the first atoms formed, setting the stage for the formation of stars, galaxies, and eventually, life itself. Imagine a universe devoid of light, where the only activity was the silent dance of particles coming together to form the building blocks of everything we know. By studying the cosmic dark age, we can gain a deeper understanding of the fundamental laws of physics that govern our universe. Researchers and astrophysicists delve into this mysterious epoch, using advanced technology and data analysis to uncover its secrets. We can learn about the conditions that led to the formation of the structures we see around us today. The galaxies, stars, and planets all have their origins traced back to this seemingly dark and silent period. The cosmic dark age is a reminder that even in darkness, the universe is constantly evolving, always changing, and full of wonder. It teaches us that from the quietest and most unassuming beginnings, the most magnificent and complex structures can emerge. This era is not just a chapter in the history of the universe. It is a testament to the incredible processes that continue to shape our reality. Section 9. Conclusion. A journey back in time. The cosmic dark age was a time of profound transformation, a period that marked the universe's transition from chaos to order. During this era, the universe transitioned from a hot, dense plasma to a cooler, more transparent state, setting the stage for the formation of the first atoms. It was a time when the first atoms formed, hydrogen and helium, the building blocks of everything we see around us today. This atomic creation paved the way for the emergence of light, allowing the first stars and galaxies to form, illuminating the cosmos. By studying this enigmatic era, astronomers are piecing together the story of our universe's evolution, a story that is as complex as it is fascinating. Through meticulous research and observation, scientists are uncovering the secrets of how the universe evolved from its dark beginnings to the vibrant, dynamic cosmos we observe today. This journey from darkness to light is not just a tale of cosmic evolution, but a testament to the incredible processes that have shaped our universe. The cosmic dark age, though hidden from our view, is a period shrouded in mystery, yet it holds the keys to understanding our cosmic origins. By unlocking the secrets of this hidden era, we gain insights into the very beginnings of the universe, shedding light on the processes that led to the formation of everything we know. The remnants of this era, such as the cosmic microwave background radiation, serve as a window into the past, allowing us to glimpse the universe in its infancy. With the help of advanced telescopes and cutting-edge technology, astronomers continue to explore this ancient epoch, revealing new discoveries that deepen our understanding of the cosmos. Each discovery adds a new chapter to the grand narrative of the universe, enriching our knowledge and inspiring future generations to look up at the stars with wonder and curiosity. Imagine the most spectacular fireworks show you've ever seen. The sky blazes with brilliant colors, sparks fly, and the air crackles with energy. Now, imagine that show on a cosmic scale, the Big Bang. This event, which marked the beginning of our universe, wasn't just an explosion of matter, but also a blinding flash of light. This light, however, didn't just disappear into the void. Like the fading embers of a dying fire, it still lingers in the universe today. We call it the cosmic microwave background, or CMB for short. It's the afterglow of creation, a faint whisper of the universe's fiery birth, still echoing through the cosmos billions of years later. Think of it this way. When you look up at the stars at night, you're essentially looking back in time. The light from those distant stars has traveled for millions, even billions of years to reach your eyes. The CMB is similar, but on a much grander scale. It's the oldest light in the universe, a direct message from a time when the cosmos was just a baby. To understand the CMB, we need to rewind the clock to the very beginning, just fractions of a second after the Big Bang. At this moment, the universe was an unimaginably hot and dense soup of elementary particles. Quarks, gluons, electrons, all zipping around at nearly the speed of light. Light itself, in the form of photons, was trapped within this chaotic mix, constantly colliding with other particles and unable to travel freely. Imagine a crowded room full of people constantly bumping into each other, unable to move freely. That's what it was like for photons in the early universe. They were constantly being scattered and absorbed, unable to escape the primordial soup. However, the universe wasn't static. It was expanding and cooling rapidly, much like the smoke and debris spreading out after an explosion. This expansion and cooling would eventually set the stage for a dramatic transformation, one that would free the light and allow it to travel across the cosmos. As the universe expanded and cooled, a crucial transition began to occur. The hot, dense soup of particles began to change. Think of it like steam cooling and condensing into water droplets. In the early universe, the cooling process allowed protons and electrons, two of the fundamental building blocks of atoms, to combine and form neutral hydrogen atoms. This period, known as recombination, was a pivotal moment in cosmic history. Before recombination, the universe was opaque, like a dense fog, because free electrons interacted strongly with light. The photons, constantly bouncing off these electrons, couldn't travel far. Imagine trying to look through a thick fog. You can't see very far because the light is scattered by the water droplets. That's what it was like in the early universe before recombination. The universe was a fog of electrons, and the light from the Big Bang was trapped within it. But with the formation of neutral hydrogen atoms, everything changed. The fog began to lift. The free electrons, now bound to protons, were no longer available to scatter photons. The universe, once opaque, became transparent. Light was free to travel unimpeded for the first time. Imagine the fog suddenly lifting, revealing a clear, bright landscape. That's what happened in the universe during recombination. The photons, no longer trapped by free electrons, were finally free to stream out into the expanding cosmos. This light, which had been trapped since the Big Bang, began its long journey through the universe. It's this very light, stretched and cooled over billions of years, that we detect today as the cosmic microwave background. Section 5. The Cosmic Microwave Background. A baby picture of the universe. The CMB is often referred to as a baby picture of the universe because it provides us with a snapshot of what the cosmos looked like when it was just 380,000 years old. Think of it this way. If the universe were a person, the CMB would be like a picture taken just hours after their birth, capturing their first moments in exquisite detail. This baby picture isn't a visual image in the traditional sense. Instead, it's a map of the temperature and density fluctuations present in the early universe. These fluctuations, though tiny, represent the seeds of the large-scale structures, galaxies, clusters of galaxies, and cosmic voids that we observe in the universe today. Just as a sonogram allows doctors to see the developing features of a baby in the womb, the CMB allows cosmologists to study the early universe and understand how the seeds of cosmic structure were sown. Section 6. Echoes of the Big Bang. The CMB is incredibly uniform, with a nearly constant temperature across the entire sky. However, it also contains tiny temperature variations, fluctuations on the order of a few millionths of a degree. These fluctuations, though seemingly insignificant, provide crucial clues about the early universe and its evolution. Imagine the CMB as a vast, calm ocean. The tiny temperature variations are like ripples on the surface of this ocean, subtle but significant. These ripples, scientists believe, were caused by sound waves, acoustic oscillations, that propagated through the early universe. These echoes of the Big Bang, imprinted on the CMB, provide us with a wealth of information about the universe's age, composition, and even its geometry. Section 7. Mapping the early universe. To study the CMB in detail, scientists have launched sophisticated space telescopes, such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite. These missions have mapped the CMB with incredible precision, revealing its subtle temperature variations in exquisite detail. Imagine trying to map the entire surface of the Earth with incredible accuracy, down to the smallest details. That's essentially what these space telescopes have done for the CMB, creating detailed maps that allow scientists to study the early universe in unprecedented detail. These maps have revolutionized our understanding of the early universe, providing strong evidence for the Big Bang theory and offering insights into the processes that shaped the cosmos into what we see today. Section 8. The secrets hidden in the CMB. The CMB is a treasure trove of information about the early universe, and scientists are still analyzing the data from missions like Planck to unlock its secrets. One of the key findings from these studies is the confirmation of the existence of dark matter and dark energy, two mysterious components that make up the vast majority of the universe's mass-energy budget. Think of the CMB as a cosmic detective story, with the tiny temperature variations providing clues to the universe's deepest mysteries. By carefully analyzing these clues, scientists are piecing together the story of the universe's first moments and its subsequent evolution. The CMB is also helping us understand the process of cosmic inflation, a period of rapid expansion in the universe's earliest moments that is thought to have stretched out any initial irregularities and created the smooth, vast cosmos we observe today. Section 9. A window to the first moments. The CMB provides us with a glimpse of the universe when it was just a tiny fraction of its current age. By studying this ancient light, we're essentially looking back in time to witness the afterglow of creation itself. It's a humbling thought to realize that we can observe and study light that has been traveling through the cosmos for almost the entirety of its existence. Imagine finding a message in a bottle that had been drifting in the ocean for centuries, containing a first-hand account of a historical event. That's what the CMB is like for cosmologists, a message from the distant past, carrying with it invaluable information about the universe's birth and infancy. By continuing to study the CMB, we hope to unravel even more mysteries about the early universe and gain a deeper understanding of our cosmic origins. Section 10. The CMB and the fate of the universe. The CMB not only tells us about the universe's past, but also provides clues about its future. By studying the properties of the CMB, such as its temperature and polarization, cosmologists can learn about the universe's geometry, its expansion rate, and the nature of dark energy, which is believed to be driving the accelerated expansion of the universe. Imagine trying to predict the future of a tree by studying its rings. The CMB is like the universe's tree rings, providing us with information about its past growth and potential future development. By understanding the forces that have shaped the universe throughout its history, we can make more informed predictions about its ultimate fate. Will the universe continue to expand forever, or will it eventually collapse upon itself in a big crunch? The CMB holds clues to these fundamental questions, and scientists continue to study this ancient light in the hope of unraveling the universe's grand destiny.
Imagine the universe just moments after its birth. Roughly 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine, forming neutral hydrogen atoms. This event filled the universe with a faint afterglow, the cosmic microwave background radiation, which we can still detect today. With the formation of neutral hydrogen, the universe entered a period known as the Cosmic Dark Ages. No stars, no galaxies, just a vast, expanding expanse of gas, shrouded in darkness. These density fluctuations, though small, were crucial. They represented regions where gravity was slightly stronger, pulling in more and more matter over time. A mysterious substance known as dark matter also played a crucial role. In the darkness of the early universe, these density fluctuations grew slowly at first. Gravity, though relentless, was weak over vast distances. Millions of years passed, and the universe continued to expand and cool. As the universe expanded, these overdense regions, dominated by dark matter, grew denser. Their gravity pulled in more and more hydrogen gas, further increasing their mass and gravitational pull. This runaway process, driven by gravity, eventually led to the formation of giant gas clouds, the birthplaces of the first stars. Within these clouds, gravity continued its work, pulling gas towards the center, increasing the density and temperature at the core. Deep within the hearts of these collapsing gas clouds, a remarkable transformation began. As gravity pulled more and more hydrogen gas towards the center, temperatures and pressures soared to unimaginable levels. Finally, after millions of years of contraction, the core of the cloud reached a critical threshold. Nuclear fusion ignited, flooding the surrounding gas with intense radiation. The first stars were born, colossal giants, hundreds of times more massive than our sun, blazing with a ferocious intensity. Their intense ultraviolet radiation ripped through the surrounding neutral hydrogen gas, stripping electrons from atoms, a process known as ionization. These first stars, however, were short-lived. They ended their lives in spectacular supernova explosions, seeding the surrounding gas with the first heavy elements. The birth of the first stars unleashed a torrent of ultraviolet radiation into the universe. This radiation, carrying immense energy, interacted with the surrounding neutral hydrogen gas, knocking electrons free from their atomic nuclei. This process, known as ionization, transformed the universe from a state of neutral hydrogen to one of ionized plasma. Before reionization, the universe was opaque to ultraviolet radiation, the neutral hydrogen gas acting like a dense fog. As reionization progressed, however, the fog began to lift, allowing light to travel freely through the cosmos. Reionization likely occurred in stages, with bubbles of ionized gas expanding around the first stars and galaxies, gradually merging to fill the entire universe. The epoch of reionization marked the end of the universe's dark ages. Light, once trapped by the neutral hydrogen fog, could now travel freely across vast cosmic distances. Section 5. Cosmic Architects: The Role of Dark Matter. While the first stars and galaxies were composed of ordinary matter, their formation was orchestrated by a mysterious and invisible force, dark matter. 5 times more abundant than ordinary matter, dark matter exerts a gravitational pull, but does not interact with light, making it invisible to our telescopes. In the early universe, dark matter's gravity acted as a scaffolding, shaping the distribution of ordinary matter. The density fluctuations that gave rise to the first stars and galaxies were amplified by dark matter's gravitational pull, drawing in vast amounts of hydrogen gas. Dark matter also played a crucial role in the formation of galaxies themselves. As gas cooled and collapsed within dark matter halos, it formed rotating disks, the precursors to spiral galaxies like our own Milky Way. Without dark matter, the universe would look vastly different. Section 6. Islands of Light: The Formation of Galaxies. As the first stars ignited, their intense radiation and stellar winds began to sculpt the surrounding gas. These early stars, clustered together in small groups, represented the seeds of what would become the first galaxies. Over time, gravity drew these stellar clusters together, merging them into larger and more complex systems. These early galaxies were much smaller and less massive than the majestic spiral and elliptical galaxies we observe in the nearby universe. Despite their small size, these early galaxies were incredibly active. Star formation rates were orders of magnitude higher than in present-day galaxies, fueled by the abundant gas available in the early universe. Section 7. A Tapestry of Light and Gravity: The Cosmic Web. The distribution of galaxies in the universe is not random. Instead, galaxies are arranged in a vast interconnected network known as the cosmic web. This web-like structure, formed by the interplay of gravity and the expansion of the universe, consists of filaments, sheets, and voids resembling a giant cosmic sponge. The filaments of the cosmic web are long, thread-like structures composed of galaxies, gas, and dark matter. These filaments intersect at massive clusters of galaxies, the densest regions in the universe. Between the filaments lie vast cosmic voids, regions of space with very few galaxies. The cosmic web is a testament to the power of gravity, shaping the universe on the grandest scales. Section 8. Echoes of the Past: Observing the Early Universe. Observing the formation of the first stars and galaxies is a challenging task. The light from these distant objects has been traveling towards us for billions of years, stretched and weakened by the expansion of the universe. To peer back to this early epoch, astronomers rely on powerful telescopes, both on the ground and in space. One of the most powerful tools in the astronomer's arsenal is the Hubble Space Telescope. Orbiting above Earth's atmosphere, Hubble can capture incredibly faint light from distant objects, allowing astronomers to glimpse galaxies as they were just a few 100 million years after the Big Bang. Another powerful tool is the James Webb Space Telescope, launched in 2021. Section 9. A Universe Transformed: The Legacy of the First Stars. The formation of the first stars and galaxies marked a profound turning point in the history of the universe. Their emergence transformed the cosmos from a dark, simple expanse of gas into a universe ablaze with starlight, filled with the building blocks of planets and life. The intense radiation from these early stars reionized the universe, splitting neutral hydrogen atoms back into protons and electrons. The first stars also seeded the universe with heavy elements, the raw materials for future generations of stars, planets, and even life. The legacy of the first stars is profound. Their impact still felt billions of years later. Section 10, Our Cosmic Origins: A Continuing Journey. The study of the first stars and galaxies is a journey through time, a quest to understand our cosmic origins. By peering back to the universe's earliest moments, astronomers are piecing together the story of how our universe evolved from a hot, dense state to the complex and diverse cosmos we observe today. The discoveries made in recent decades have revolutionized our understanding of the early universe. We now know that the first stars were massive, short-lived giants, responsible for ending the cosmic dark ages and seeding the universe with heavy elements. The journey, however, is far from over. Many questions about the early universe.
The universe began as a sea of darkness. Then, gravity worked its magic. It pulled together vast clouds of hydrogen and helium, the simplest elements. These clouds collapsed under their own weight, growing hotter and denser. Finally, they ignited, bursting into brilliant light. The first stars were born. These early stars were giants, much larger and hotter than our sun. They lived fast and died young, exhausting their nuclear fuel in just a few million years. But their short lives had a profound impact on the universe. Within the fiery hearts of these stars, a remarkable transformation took place. The intense heat and pressure of the stellar core acted like a cosmic furnace, fusing hydrogen atoms together to create helium. This process, known as nuclear fusion, released enormous amounts of energy, powering the stars and flooding the universe with light. As the first stars aged, their cores became even hotter and denser. The helium atoms, forged from hydrogen, began to fuse as well, creating heavier elements like carbon, oxygen, and nitrogen. These elements, essential for life as we know it, were born in the fiery hearts of dying stars. Each stage of fusion released more energy, temporarily staving off the star's inevitable collapse. But eventually the star's core transformed into a dense ball of iron. Iron, the most stable of all elements, cannot be fused to create heavier elements. At this point, the star's fate was sealed. The outward pressure from nuclear fusion could no longer counteract the immense gravity of the star's core. The core collapsed in on itself, triggering a cataclysmic explosion that ripped the star apart. Supernovae are among the most violent events in the universe. In a fraction of a second, a single star releases more energy than our sun will in its entire lifetime. This energy blasts the star's outer layers into space at incredible speeds, scattering the elements forged in its core far and wide. These scattered elements, enriched with carbon, oxygen, nitrogen, and other heavy elements, became the seeds for future generations of stars and planets. They drifted through the vastness of space, eventually becoming part of new interstellar clouds. The shock waves from supernovae also played a crucial role in triggering the formation of new stars. As these shock waves traveled through interstellar clouds, they compressed the gas and dust, kickstarting the gravitational collapse that would lead to the birth of new stars. Within these interstellar clouds, enriched with the elements forged in the hearts of dead stars, the stage was set for the formation of planets. Gravity drew together clumps of gas and dust, gradually forming larger and larger objects. As these objects grew, their gravitational pull increased, attracting even more material. Over millions of years, these clumps transformed into planets, their composition reflecting the elements present in the surrounding nebula. The heavier elements, like iron and silicon, formed the rocky cores of planets. Lighter elements like hydrogen and helium created the atmospheres of gas giants, and in a select few planetary systems, the conditions were just right for the formation of something truly extraordinary: life. Section 5. The breath of stars. Elements, essential for life. The elements forged in the hearts of stars and scattered by supernovae are not just the building blocks of planets, they are the very elements that make life possible. Carbon, the backbone of all organic molecules, allows for the complexity and diversity of life as we know it. Oxygen, breathed in by countless organisms, is essential for respiration, the process that releases energy from food. Nitrogen, a key component of DNA and amino acids, is crucial for heredity and protein synthesis. These elements, and many others, are the legacy of stars, woven into the very fabric of life. Every breath we take, every bite of food we consume connects us to the vast cosmic web of starbirth, life and death. We are, in a very real sense, children of the stars, formed from the same elements that light up the night sky. Section 6. A cosmic cycle, the circle of stellar life and death. The death of a star is not the end but rather a new beginning. The elements scattered by supernovae eventually become part of new interstellar clouds, enriching them with the building blocks for future generations of stars and planets. This cycle of star formation, life, and death has been repeating for billions of years, gradually enriching the universe with heavier elements. Each generation of stars builds upon the legacy of its predecessors, contributing to the ever-increasing complexity of the cosmos. The stars we see in the night sky today are not the same stars that shone billions of years ago. They are their descendants, formed from the ashes of their ancestors. And just as stars are born from the remnants of previous generations, so too will our sun eventually meet its end, seeding the galaxy with the elements for new worlds and new possibilities. Section 7. Stellar Nurseries, where new stars take shape. Within vast clouds of interstellar gas and dust, known as nebulae, gravity continues to work its magic. These nebulae, enriched with the elements forged in the hearts of dead stars, serve as stellar nurseries, where new stars are born. As gravity pulls together clumps of gas and dust within these nebulae, they heat up and begin to glow, forming protostars. Over millions of years, these protostars continue to accrete material, eventually becoming hot and dense enough to ignite nuclear fusion in their cores. The birth of new stars lights up the nebulae, creating breathtaking displays of cosmic beauty. These stellar nurseries showcase the ongoing cycle of star formation, reminding us that the universe is a dynamic and ever-evolving place. Section 8. The Sun's Legacy, our star's role in life's story. Our own sun is a third-generation star, formed from the remnants of stars that lived and died billions of years ago. The elements forged in those ancient stars are now part of our planet, our bodies, and everything around us. The sun's energy, generated by nuclear fusion in its core, sustains life on Earth. Plants use sunlight to create food through photosynthesis, providing energy for themselves and the animals that eat them. The sun's warmth drives our weather patterns, ocean currents, and climate. Our sun is more than just a star. It is the lifeblood of our planet, providing the energy and warmth that make our existence possible. And though our sun will eventually reach the end of its life, its legacy will live on in the elements it scatters into space, potentially contributing to the formation of new worlds and new life. Section 9. Cosmic Connections, the universe within us. We are all connected to the cosmos in a profound way. The elements that make up our bodies were forged in the hearts of stars that lived and died long ago. Every atom in our being has a cosmic history, tracing back to the Big Bang and the birth of the universe. When we look up at the stars, we are looking at our own origins. We are witnessing the processes that created the elements that make life possible. We are part of a grand cosmic cycle, connected to the universe on a fundamental level. Understanding our cosmic connections fosters a sense of wonder and awe at the vastness and complexity of the universe. It reminds us that we are not isolated beings but rather integral parts of a vast and interconnected cosmos. Section 10. A universe of possibilities, the search for life beyond Earth. The discovery that the elements of life are widespread throughout the universe raises profound questions about the possibility of life beyond Earth. If the ingredients for life are common, then perhaps life itself is not unique to our planet. Scientists are actively searching for signs of life on other planets, looking for evidence of water, organic molecules, and other biosignatures. The discovery of even the simplest extraterrestrial life would revolutionize our understanding of our place in the universe. The search for life beyond Earth is a testament to our innate curiosity and our desire to explore the unknown. It is a journey driven by the hope of discovering that we are not alone in the vastness of the cosmos. Section 11. Our place in the cosmos, reflections on stars and humanity. As we contemplate the vastness of the universe and the interconnectedness of all things, we are filled with a sense of wonder and humility. We are but a small part of something much greater than ourselves, a cosmic story billions of years in the making. The study of stars and the universe helps us to understand our place in the cosmos, both our insignificance in the grand scheme of things, and our remarkable ability to comprehend the universe around us. It is a journey of discovery that inspires us to learn more about ourselves and the world we inhabit. As we continue to explore the cosmos, we carry with us the knowledge that we are children of the stars, products of a universe teeming with wonder and possibility. And as we strive to understand the universe and our place within it, we are reminded of the preciousness of life and the importance of safeguarding our planet for future generations. Imagine a time when there was nothing. No light, no sound, just an endless void of darkness. No stars, no planets, not even space itself. It was a time before time, a place before place. Then, about 13.8 billion years ago, bang! The Big Bang happened. In an instant, everything changed. It was a massive explosion of energy and light, a burst so powerful that it set the stage for everything we know today. This event marked the beginning of our universe. From that single moment, the cosmos began to take shape. It was incredibly hot and dense at first. Temperatures soared to unimaginable levels and the density was beyond comprehension. But as the universe expanded, it cooled down. This cooling process was crucial for the formation of the first particles. This cooling allowed tiny particles to form. These particles were the building blocks of everything that would come later. These particles eventually clumped together to create the first atoms. It was a slow and gradual process, but it was the beginning of matter as we know it. The most common atoms were hydrogen and helium. These simple elements were the first to form in the young universe. These atoms are still the most abundant elements in the universe today. They are the fundamental building blocks of stars, planets, and even life itself. They became the building blocks for everything else. From these humble beginnings, the universe began to grow and evolve. The universe continued expanding and evolving. Over billions of years, it transformed into the vast and complex cosmos we see today. Over millions of years, gravity started to pull these atoms together. This force of attraction was the key to forming larger structures. These clusters of atoms would eventually become the seeds of stars and galaxies. Gravity continued to shape and mold the universe. The universe was transforming from a sea of particles into a tapestry of cosmic structures. Stars ignited, galaxies formed, and the universe became a place of wonder and beauty. Today we look up at the night sky and see the legacy of that incredible explosion. The universe is a testament to the power and beauty of creation. From the smallest particles to the largest galaxies, everything we see is a part of this grand cosmic story. Our universe, born from a single moment of creation, continues to expand and evolve, filling us with awe and wonder. Fast forward millions of years. The universe was filled with giant clouds of gas and dust. These clouds were like enormous cosmic dust bunnies. They were mostly made up of hydrogen and helium, left over from the Big Bang. Scattered within these clouds were heavier elements. These elements were forged in the fiery hearts of early stars. These clouds, called nebulae, were the birthplaces of stars. Within these swirling clouds, gravity worked its magic. It pulled the gas and dust particles together. As these particles collided, they generated heat. The clouds became denser and hotter over time. These stellar nurseries were about to get a whole lot brighter. Deep within one of these nebulae, something spectacular began to happen. Gravity started to pull most of the gas and dust towards the center. As more and more material clumped together, the clouds started to spin. Imagine a figure skater pulling their arms in during a spin, rotating faster and faster. This spinning motion caused the cloud to flatten into a disc. Think of it like a spinning pizza dough, stretching out as it rotates. At the center of this disc, the material became incredibly dense and hot. This hot, dense center would eventually become our very own star, the Sun. The core of the collapsing cloud became a furnace. The pressure and temperature soared. Atoms were smashing into each other with incredible force. This intense pressure and heat triggered a process called nuclear fusion. Hydrogen atoms fused together to form helium, releasing an enormous amount of energy. And just like that, the Sun was born. It blazed to life, illuminating the surrounding disk of gas and dust. Our solar system now had a star at its center, bathing everything in its light and warmth. But the story doesn't end there. The leftover material from the Sun's formation had a crucial role to play. Section 5, From Pebbles to Planets, Accretion in Action. While the Sun was busy igniting, the remaining gas and dust in the disk were not just sitting still. They were in constant motion, swirling around the newborn star, creating a dynamic and ever-changing environment. These particles were constantly bumping into each other like a cosmic dance of tiny grains. Each collision was a chance for something new to form. Sometimes they would stick together like cosmic dust bunnies gathering under a couch. This sticking process was crucial, as it allowed the particles to grow larger over time. Over millions of years, these tiny particles grew bigger and bigger. What started as microscopic grains eventually became larger clumps, and these clumps continued to merge and grow. This process, called accretion, is how planets are formed. It's a slow but steady accumulation of material, driven by gravity and the natural tendency of particles to stick together. Small particles combine to form pebbles, then boulders, then planetesimals, and eventually, planets. Each stage of growth brought new challenges and opportunities for the developing bodies. Closer to the Sun, where it was hotter, rocky planets like Earth and Mars formed. The intense heat caused lighter elements to evaporate, leaving behind heavier, rocky materials. Further out, where it was colder, gas giants like Jupiter and Saturn formed. In these frigid regions, ice and gas could accumulate, leading to the creation of these massive planets. The differences in temperature and material availability across the solar system played a key role in determining the types of planets that formed in different regions. Section 6 Earth, our pale blue dot. In the grand tapestry of the universe, our planet holds a unique and precious place. In the vastness of space, a small, rocky planet formed. This planet, amidst countless others, began its journey over 4.5 billion years ago. That planet was Earth, our home, a place where life would eventually flourish in ways unimaginable. Earth formed in what we call the habitable zone, this special region around a star where conditions are just right for life. This zone is the perfect distance from the Sun for liquid water to exist on a planet's surface. Neither too hot nor too cold, it provides the ideal environment for sustaining life. And as we know, water is essential for life as we know it. It is the lifeblood of our planet, nurturing every living organism. Over billions of years, Earth transformed into the planet we know and love today. Oceans formed, continents shifted, and the atmosphere evolved to support a diverse array of life forms, and life emerged in its incredible diversity. From the simplest microorganisms to the most complex ecosystems, life on Earth is a marvel of evolution. The formation of Earth, a haven for life in the vastness of space, is a testament to the awe-inspiring power of cosmic processes. It reminds us of the delicate balance and intricate dance of elements that make our existence possible. Section 7. Leftovers of creation, comets and asteroids. Not all of the material in the early solar system ended up forming planets. Some of it remained scattered between the planets, like leftover crumbs after a cosmic feast. These remnants became asteroids and comets. Asteroids are rocky bodies, while comets are icy bodies. These cosmic wanderers provide valuable clues about the early solar system. They contain material that has remained largely unchanged since the solar system's formation. Studying them is like looking back in time, offering insights into the conditions that led to the creation of our planetary neighborhood. Section 8. The Solar System, our cosmic neighborhood. So there you have it. From a giant swirling cloud of gas and dust, our solar system was born. A star ignited at the center, planets formed from leftover material, and asteroids and comets took up residence in the spaces between. Our solar system is a dynamic and fascinating place. Each planet has unique characteristics and stories to tell. From the scorching heat of Venus to the icy rings of Saturn, our solar system is full of wonder and beauty. And it all started with a cloud of gas and dust billions of years ago. Section 9. A universe of possibilities. Our solar system, while vast and awe-inspiring, is just one tiny part of the universe. Astronomers believe that there are billions of other galaxies out there, each containing billions of stars. Many of those stars likely have their own planetary systems, just like ours. This realization opens up a world of possibilities. Could there be other planets out there that harbor life? Could there be other intelligent civilizations looking up at the same stars and wondering the same things we do? The search for answers to these questions continues to drive our exploration of the cosmos. Section 10. The Enduring Mystery. The formation of our solar system is a story billions of years in the making. It's a story of cosmic collisions, gravitational dances, and the incredible power of nature to create order out of chaos. But it's also a story with many chapters yet to be written. As we continue to explore and learn more about our universe, we uncover new mysteries and deepen our understanding of our place within it. The quest to unravel the secrets of the cosmos is a journey that continues to inspire and captivate humanity.
The universe is a vast and ever-changing place. It's filled with billions of galaxies, each containing billions of stars. What's even more amazing is that the universe is not static, it's constantly expanding, pushing those galaxies farther and farther apart. Imagine baking a loaf of raisin bread. As the dough rises, the raisins embedded within it move away from each other. That's kind of what's happening in our universe. The galaxies are like the raisins, and the expanding space is like the rising dough. This expansion was a groundbreaking discovery that changed our understanding of the cosmos. It means the universe was once much smaller and denser than it is today. It also raises profound questions about the ultimate fate of everything we see around us. In the 1920s, astronomer Edwin Hubble made a remarkable observation. He noticed that galaxies are moving away from us. Not only that, but the farther away a galaxy is, the faster it's receding. This relationship between distance and speed is now known as Hubble's law. Hubble's discovery provided the first concrete evidence that the universe is expanding. It's like watching dots on a balloon move apart as you inflate it. Each dot represents a galaxy, and the expanding balloon represents the fabric of space-time itself. Hubble's law has become a cornerstone of modern cosmology. It allows astronomers to measure the distances to faraway galaxies and estimate the age of the universe itself. It also provides a crucial clue for understanding the forces at play in the cosmos. Within the vast and ever-expanding universe, a cosmic dance of creation and destruction is constantly taking place, shaping the very fabric of our cosmos. Galaxies are not just moving away from each other, they're also interacting and evolving in fascinating and complex ways, driven by gravitational forces and cosmic events. Sometimes galaxies collide in spectacular events that trigger bursts of star formation, lighting up the universe with new stars. These mergers can reshape entire galaxies, creating new structures and altering their destinies, often leading to the formation of new star systems and planetary bodies. Our own Milky Way galaxy is on a collision course with our galactic neighbor, Andromeda, a cosmic event that will unfold over billions of years. Meanwhile, within galaxies, stars are born, live out their lives, and eventually die, each stage contributing to the cosmic cycle. Some stars end their lives in dramatic explosions called supernovae, which can outshine an entire galaxy for a brief time, releasing immense energy. These explosions seed the universe with heavy elements, the building blocks of planets and life, enriching the interstellar medium. At the end of their lives, massive stars can collapse under their own gravity, forming incredibly dense objects called black holes, which are among the most mysterious phenomena in the universe. These cosmic monsters warp space-time so strongly that nothing, not even light, can escape their gravitational pull, creating regions of space where the laws of physics as we know them break down. While gravity pulls things together, something seems to be pushing the universe apart at an accelerating rate. This mysterious force, known as dark energy, is one of the biggest puzzles in modern cosmology today. We don't know what dark energy is made of, or how it works exactly. But we do know that it makes up about 70% of the total energy density of the universe. Its presence has profound implications for the fate of the cosmos. Some scientists believe that dark energy is a property of space itself. Others think it might be a new type of energy field that we don't yet understand fully. Whatever it is, dark energy is a powerful force that's shaping the evolution of the universe on the grandest scales imaginable. Section 5, The Big Freeze, a chilly end to the cosmos. The future of the universe depends largely on the nature of dark energy. If dark energy continues to drive the expansion of the universe at an accelerating rate, as it seems to be doing now, then we might be headed for a big freeze. In this scenario, the universe will continue to expand and cool indefinitely. Galaxies will drift farther and farther apart, eventually becoming isolated islands in the vast cosmic void. Stars will eventually burn out, leaving behind only faint remnants. The universe will become a dark, cold, and desolate place, with matter and energy spread so thinly that it would be virtually impossible to detect any signs of life or activity. The Big Freeze is a bleak but plausible end to the universe as we know it. Section 6, the Big Crunch, a universe collapsing inward. Another possible fate for the universe is the Big Crunch. This scenario is essentially the opposite of the Big Freeze. Instead of expanding forever, the universe could eventually stop expanding and begin to contract. If the density of matter and energy in the universe is high enough, gravity could eventually overcome the outward push of dark energy. The expansion would slow down, stop, and then reverse. Galaxies would start moving closer together, eventually colliding and merging in a fiery cataclysm. As the universe collapses, temperatures would rise dramatically, stars would explode, black holes would merge, and eventually all matter and energy would be compressed into a single, infinitely dense point, a singularity. This scenario is a dramatic and violent end to the universe, but it's also a possibility that cannot be ruled out. Section 7. The Big Rip, when space-time tears apart. Perhaps the most dramatic and unsettling fate for the universe is the Big Rip. In this scenario, dark energy doesn't just drive the expansion of the universe, it rips it apart. If dark energy's strength increases over time, it could eventually become so powerful that it overcomes all other forces in the universe, including gravity and the forces that hold atoms together. Galaxies would be torn apart, followed by stars, planets, and eventually even atoms themselves. The fabric of space-time would be shredded, leaving behind a chaotic and utterly alien realm where the very laws of physics might cease to exist. The Big Rip is a truly mind-boggling concept, but it's a theoretical possibility that some physicists take seriously. Section 8. Other possible fates, a multiverse, and more. Beyond the well-known scenarios like the Big Freeze, Big Crunch, and Big Rip, there are other, even more exotic possibilities that scientists have theorized for the ultimate fate of the universe. Some of these theories suggest that we might actually live in a multiverse, a vast and almost incomprehensible collection of universes, each one potentially having its own unique set of physical laws and constants that govern its behavior. In this fascinating scenario, our universe might be just one bubble in a much larger cosmic foam, a tiny part of an enormous and complex multiverse. Another intriguing possibility is that the universe undergoes cycles of expansion and contraction, a concept known as the Big Bounce. In this model, the Big Bang might not represent the absolute beginning of everything, but could be a transition point from a previous phase of the universe, leading to a continuous cycle of rebirth. These theories are highly speculative and remain the subject of intense debate and research, but they highlight the incredible diversity of thought and imagination that exists within the field of cosmology. They also underscore the sheer wonder and curiosity that drive scientists to explore the cosmos. As we continue to probe the mysteries of the universe with ever more advanced technology and innovative methods, we're likely to uncover even more fascinating and unexpected possibilities, expanding our understanding of the cosmos in ways we can scarcely imagine today. Section 9. The Unknowable Future, a Universe of Possibilities. The ultimate fate of the universe is a question that has captivated astronomers, physicists, and philosophers for centuries. While we've made incredible strides in understanding the cosmos, the future remains shrouded in uncertainty. The answer likely lies in the nature of dark energy, a force we barely understand. Its properties will ultimately determine whether the universe continues to expand forever, collapses back in on itself, or meets some other, even more exotic fate. The good news is that we have plenty of time to unravel these mysteries. The timescales involved in the ultimate fate of the universe are vast, billions if not trillions of years in the future. In the meantime, we can marvel at the wonders of the cosmos and continue our quest to comprehend its deepest secrets. Section 10. Our place in the cosmic tapestry. As we contemplate the vastness of the universe and its uncertain future, it's humbling to consider our own place in this grand cosmic tapestry. The sheer scale of the cosmos, with its billions of galaxies, each containing billions of stars, is almost beyond comprehension. We are, after all, just a small part of something much larger than ourselves. Our planet, Earth, is but a tiny speck in the vast expanse of space, orbiting a relatively average star in an unremarkable galaxy. Yet, we are also a product of this universe, forged from the same stardust that makes up everything we see around us. The atoms in our bodies were formed in the hearts of ancient stars that lived and died long before our solar system was born. And in a sense, we are the universe trying to understand itself. Through our observations and explorations, we seek to unravel the mysteries of our origins and our place in the cosmos. Our curiosity, our ingenuity, and our relentless pursuit of knowledge are all testaments to the extraordinary power of the human spirit. From the earliest astronomers who mapped the stars to modern scientists who send probes to distant planets, our quest for understanding has always driven us forward. While we may never know for certain what the future holds for the universe, we can take comfort in knowing that we are part of something truly awe-inspiring. The universe is a place of endless wonder and infinite possibility. And as we continue to explore the cosmos and unlock its secrets, we can be sure that the universe will continue to surprise and amaze us. Each new discovery brings us one step closer to understanding the grand tapestry of existence and our unique place within it.